Good afternoon, everyone. Today I will give a topic of my recent research. It is about how to fully exploit the window carapace to aid the GNSS positioning in urban canyons. Okay, let's begin. And these two figures shows that the GNSS positioning face very large challenges in urban areas. So, and this figure shows that there is dense traffic and the tall and dense buildings, and they will reflect or block the GNSS signals. So, the positioning performance may be become degraded in urban areas. So, how to improve the GNSS positioning in urban areas? That's what we want to do. And next, before I introduce the method, I want to show you the table about the comparison between the signal range and the carapace measurement. Firstly, we can say when the signal range measurement is used, the receiver noise can even reach 30 centimeters. And so when the carapace is fully used, the receiver noise can be reduced to the almost the millimeters level. So it improves a lot. So we realized a very important thing that the carapace measurement should be fully exploited to help GNSS positioning in urban canyons. But there is an unknown ambiguity in the carapace measurement. It's an unknown variable, and it needs to be estimated when use the carapace measurement. So the carapace measurement can be directly used, obviously. So the straightforward use the carapace is to do the difference between the two consecutive epochs. And the figure shows that when the user and the epoch T0, they can receive the signal and this one. And when the user moves to the T1, and then he can receive the signal in this one. And and the time difference carapace, short for TDCP, shows that they can minus these two epoch measurement, and then we can go to the theta one, and then the theta one we can find that there is no unknown variable. That's the integer ambiguity n. So now the question is how to use this TDCP in FGO. Wait a moment. Okay. So this is a conventional method that we previously mentioned, the TDCP, time difference the carapace. Okay, it is by differences two carapace measurements in two consecutive epochs, and to reduce the unknown variable integer ambiguity. So as we can see from the factor graph structure, we noticed that this gray rectangle, it shows the Doppler velocity factor. We found that it can connect the consecutive two epochs, and the cross correlation matrix shows that it is very sparse. And so when the TDCP is introduced, it denotes by the blue rectangle, shows that it is a TDCP factor. So when the TDCP is used, we can also find that the cross correlation matrix, it is very sparse. It only considers the two neighboring epochs, and the time correlation between the multiple epochs are not fully exploited. So this is a TDCP measurement modeling. In the next, I want to quickly go through how to derive the TDCP factor. Firstly, okay, this is a carrier phase measurement. Lambda is the wavelength, and this is a geometric range. This is clock bias and the atmosphere effects and the carrier phase bias and the correction terms, the other errors. Okay, we noted that the carrier phase bias include the integer ambiguity. Okay, that's a unknown variable. We need to estimate it if you use the carrier phase measurement. But also it depends on the method, which one you used. So, okay. Then the TDCP measurement modeling is based on by differences the two carrier phase measurement between the consecutive epochs, and this formulation shows, and we found that the integer ambiguity is reduced. And next, based on the formulation, we can derive the TDCP factor, and this formulation shows. And this is the covariance matrix. Okay, this is a carrier phase measurement observation measurements. This is estimated measurements, and then we can derive the TDCP factor. So there is a large limitation for this method. Because we noticed that from the cross-correlation matrix, the TDCP only considers the two neighboring epochs. So again, the time correlation is not fully used. So we want to exploit the multiple epochs and to improve the robustness of positioning. So according to the nature of the GNSS tracking loops, the integer ambiguity tends to be constant when the satellite is effectively tracked. So based on this, we proposed our method, window carrier phase. So, and this factor graph structure shows that the window carrier phase can connect the multiple epochs measurements from one satellite. So, as right correlation matrix shows that the matrix become dense from the very sparse. Okay, so that means the WCP can exploit the kinematic time correlation between the multiple epochs. This is the framework of our proposed method. Okay, until now, we know how to derive the window carrier phase factor, and as for the other factor, such as the signal range or the Doppler velocity, we are not explained here. So we focus on the window carrier phase factor. Okay, in the previous slide, you have already know what the carrier phase measurement look like from one satellite and one epoch. So now, when we stack multiple carrier phase measurement together, and then we can go to this formulation. Okay, here for simplicity, we model the clock bias and the atmosphere effects and the correction terms together in the M. Okay, the superscript S denotes the satellite. The the R denotes the receiver, and NKS denotes the satellite is tracked continuously for how many times. And next, we wanna rewriting this formulation like this one. because based on the assumption, when the satellite is continuously effectively tracked, we think the integer ambiguity keeps constant. So we think they are same. So we can get this formulation. And next, there is very important part. We propose a method called left non-space matrix, and then we multiply the left non-space matrix into sides. Then we can find this term is reduced. So now we do not worry about the integer ambiguity at all anymore. And okay, and for the how to calculate the left non-space matrix, there is a this is a very mathematic process. So the step-by-step details has shown in my manuscript. If you are interested, you can see the appendix in my manuscript. But one thing is that the left non-space matrix is not unique, and you can, according the calculation method, you may get several candidates, such as matrix. Okay, in the next, then we know how to formulate the window carrier phase measurement, and then the window carrier phase factor can also be derived, and this formulation shows. This is a covariance matrix. And now let's take a very short comparison. Okay, we can see between the window carrier phase and the TDCP, we can say the window carrier phase aided by left non-space matrix to reduce the integer ambiguity, but also has an assumption that the satellite is effectively tracked in multiple epochs, so the integer ambiguity keeps constant. In view of that, we can use the left non-space matrix, and this formulation shows that. Okay, for the TDCP, it does the difference between the two epochs. Okay, then the integer ambiguity can be reduced. And next, we can also, from the cross-correlation matrix, say their difference. Okay, for the window carrier phase, the matrix is very dense. That means the time correlation between multiple epochs is fully used. But for the TDCP, we found that the matrix is very sparse. It only considers the two neighboring epochs. Okay. Actually, interestingly, the TDCP can be a special format of the window carrier phase constraint with a window size of 2. So when the assumption is no longer hold on, that means so when the partition cycle slip happens, the assumption no longer holds on. So what should we do? And in our research, we proposed the method called we use the M estimator to mitigate the effects caused by the cycle slip. Okay, this is a different kinds of M estimator, and we found that this is the normal square loss function. Okay, the red one and the blue one, it is a different M estimator with different kernel values. Okay, the kernel values control the shape. When we choose the different kind of M estimator with different kernel value, and they will mitigate the effects of cycle slip by different level. And we can say if there is a light residuals caused by the cycle slip, And then we found that if we use the square loss function, and then there is very large loss, and then it will maybe lead to the positioning degeneration. And so if we use the M estimator, and then we find that if there is a large residuals, then we can find the M estimator can reduce the large loss into here. It can control the loss. So that's why we use the M estimator to detect and mitigate the effects of cycle sleep. And later I will show you how to choose the suitable M estimator with the kernel values. And to this part, we know how to derive the TDCP factor and how to derive the window carrier phase factor, and what's the difference between them. So as for the signal range factor and the Doppler factor, we do not talk too much. So you can maybe you are familiar with them already. So if you are interested in the more details, you can also see the manuscript. Okay, here, let's take a conclusion. And then we derived the factor here, the Doppler and signal range and the window carrier phase factor. Then we can minimize them based on the factor graph optimization. Then we can go to the optimized state. Okay, next, let's say we conduct at least two experiments to validate our proposed method. Okay, and the figure shows that this is our experimental setup. We use the span CPT to provide the ground truth, and this U blocks MAT to receive the GNSS signals. And also we used a smartphone level receiver to validate our proposed method. Okay, that's all about the setup. And then we conduct the two experiments in the Urban Canyon 1 and Urban Canyon 2. The red curve shows the trajectory. And in order to validate our proposed method, we compare the listed 5 methods. Okay, first one is the U-block solution, and the second one is the V-list square, and the third one is signal range, loosely coupled with the Doppler measurement based on factor graph. And the fourth one is signal range Doppler integrated with the TDCP factor based on the factor graph. And the third and the last one is our proposed method, the signal range and Doppler and the window carrier phase measurement integration. Okay, let's see the experiments firstly in the Urban Canyon 1. And this figure shows that we can see that the blue one denotes our proposed method. The positioning performance overall is better than other method. Okay, and the table shows that the U blocks, the mean error for U blocks can reach about 6 meters. But when with the help of our proposed method, the mean error will decrease to about 1 meters. The improvement of our proposed method can reach about 17% compared to the method of U blocks. It is almost a level accuracy. And for more details, we can see from the right the trajectory. And the epoch B shows that it corresponding to this figure. You can see this is the intersection with tall buildings around the scenario. And in this scenario, the wait list square is larger than 10 meters, but the proposed method can reach about 4 meters. It also has a very good performance. In the epoch A, it corresponding to this scenario. There are a number of trees. Okay, the width least square can reach about 3 meters, and the proposed method can reach 2 meters. Okay, and so in next, where there is also a very important thing to explain. So how to determine the window size. So this figure shows that we set a couple of value to say the performance to say the performance of positioning using different window carrier phase. Okay, this denotes the maximum window size, and we can find when the window size set at 6, the mean error can reach 1.76 meters. But when the window size slightly increase to 9, we find the mean error is slightly improved. Okay, when we continue to increase the window carrier phase, we find that the mean error conversely increase from the 1.76 to the 1.93 meters. So we found that when we slightly increase the window, the mean error is slightly decreased because the larger or the suitable window size enables a stronger correlation between the states. But when the window size become very large, then the mean error conversely increase. That's because the potential cycle slip, which will violate the shared integer ambiguity. In other words, our assumption no longer holds on. So that's why the error increase. And we also can know that too large a size doesn't necessarily lead to the better results. So in another thing is that how we choose the proper M estimator. Okay, we said this area is free of cycle slip area because in this area the residual is very small, but in both sides the large residuals will become very large, even can reach 15 meters. And so, okay, this is just illustration, not experimental results. So we want to use this figure shows that how to mitigate the cycle slip caused the large residual. Okay, we want to say the M estimator with different kernel value where how to affect the positioning performance. Okay, and this table shows that the Hilbert already failed, but the Cauchy function has a good performance. And when the kernel value set 4, then the mean error is outperformed the other M estimator with the kernel value. Okay. So in our experiment, we choose the Cauchy function with the kernel value 4 here. And next, we also can see from other view, from the residuals view, we found that the Cauchy function can control the residuals within very small period. But for the Hilbert function, there is a long tail with large seizures. So that's also why we choose the Cauchy function here. And next, we will move to the experiments 2 conducted in urban canyon 2. Firstly, let's see the positioning performance. Our proposed method also has the overall good performance than the other method, and the blue curve shows that. And the table shows that we can say the mean error for the U blocks is about 31 meters. And with our proposed methods help, the mean error can decrease to about 3 meters. It is very large improvement. It's almost 19% compared to the method of U blocks. Okay. We can also see from the trajectory, the red one shows the U blocks. It already has a very serious deviation here. So that's why the mean error is also increased. Okay, before we use the commercial receiver, besides we use the commercial receiver, we also use the smartphone level receiver. And this shows that the smartphone also have a good performance with under our proposed methods help. And this performance of listed four methods in the urban canyon shows that the mean error can decrease from 40 meters to about 7 meters, and the improvement of our proposed method can reach 48% compared to the method of V-least square. Here we didn't use the NEMA solution from the fall, because the NEMA solution is based on many additional information, such as the inertial MU or the map matching and so on. So we just remove that. We only compare the listed four methods. Okay, let's take a brief summary. And the software problems in our research, we explore the time correlation between multiple epochs carrier phase measurements, and but there is still a limitation. That's we rely on the assumption of constant integer ambiguity for the continuously observed carrier phase measurements. So in the future work, we will also explore how to detect the cycle slip of the carrier phase measurements in urban canyons. Actually, there are also additional information. I put it in the appendix. So when we discussion, I can show you. Okay, that's all. Thank you.